Hello, my name is Alex Lagrassa, and the title of my talk is Planning with Model Preconditions for Water Manipulation. Although deformable objects are difficult to model, model-based planning is still a useful tool for many tasks involving deformable objects. For example, pouring, shaping dough, rope manipulation, and cloth smoothing. In this example, the robot is watering the houseplant and it can't spill water on the floor. For a movement in free space, using a controller that's slow enough to avoid sloshing, a simple rigid body model is accurate enough to model the effects. However, if the robot is pouring the water over the leaves, a more complex model such as a simulator is necessary to model the interactions between the water and the leaves. The task can be completed without modeling those interactions by using a special purpose model such as a simple learned model or analytical model for pouring near the base. Our problem statement is then to learn model preconditions for various different models and also use that information to plan and use models where they are accurate. To do this, we use model preconditions, which are regions of state action space where a model is predicted to be accurate. For example, transition A is not accurately modeled by any of these models. B can be accurately modeled with a simulator, and C can be modeled using a simulator or a learned model. In this work, we learn a model using data, then learn the corresponding model precondition, and then finally plan using those model preconditions to only use transitions that are predicted to be accurate. The tool we use is a model deviation estimator, or MDE. An MDE predicts the deviation, which is defined as the distance between the predicted next state of a model and the actual next state. The model precondition is then defined as state action pairs where the probability that the deviation is greater than a maximum deviation, Dmax, is less than some small probability delta. This is the data collection pipeline we use in this work. The system is in an initial state, has some initialized models, and a goal distribution. The robot computes plans, executes those plans, and then collects two data sets, alternating left and right. The first data set is to train a dynamics model. Once the models are updated, then new plans are computed, executed, and then used to update the model deviation estimators. And the final result is a planner that can compute plans that are more reliable at test time. This is the process for learning MDEs. The implementation that we use for the MDE is a Gaussian process, where the observations are inputs of state action pairs, and the outputs are the deviation. This is the domain that we evaluate our method on. The state is the pose of the box on the left and the volume of both containers. The actions are to move the left box to a desired XZ pose and to rotate about the XZ plane. The tasks are box at location, which is to move the control box to a given location, and water in box, which is to pour a given volume of water into the target container. No more than 1% of the initial volume of water can be spilled. It occurs in box at location when the box hits the target box and then water spills. Model error occurs in water in box in transport by moving too quickly and the water coming out, but also by not pouring the desired amount. Here we show the success rate in finding plans using model preconditions and without using model preconditions. On the left, you can see that the success rate in finding plans does go down using our method, and that's because it's more constrained. However, we do find that the success rate when executing those plans is much higher when using model preconditions than when not using them. In conclusion, we've shown an improvement in plan performance by using these learned model preconditions, and that deviation estimators can be used on learned models. Our next steps are to scale to larger dimensional state spaces, which are important for representing many deformable objects, and to assess the ability for this approach to improve data efficiency over existing methods, especially over predicting error in state space. We also anticipate many challenges in applying this to the real world, as data is much more expensive and the state is difficult to observe. If you're interested in discussing this further, please visit my poster or contact me. My email is on the bottom right. Thank you.